And so let's look at that. So RF is equal to the torque, and we call the torque tau, and it'd be foot-pounds force. And so we could rewrite that equation, bhp is equal to 2 pi times the torque n over 33,000. And if I want this in watts, W dot B is equal to 2 pi tau n in watts, where n is in revs per second and tau is in Newton meters. So if I measure the torque in Newton meters, this is a force times the distance r, Fr. We end up with the same thing. Now I'd like to look at example 13.8. You may want to read the example problem because it has all the language in it, and basically this has all sorts of stuff in terms of language that you might encounter when finding out information about an actual engine. So I have, it's a spark ignition engine. So that tells me that it's an Otto cycle. So the Otto cycle would tell me the theoretical cycle involved. We're going to have 6 cylinders. The H sub RP is equal to 19,000 BTUs per pound mass. It's turning at 3,000 RPM. The bore and stroke, so I have a 3.5 inch by 3.5 inch bore and stroke. And it gives us that the brake specific fuel consumption. So we have the brake specific fuel consumption. Brake specific fuel consumption is equal to 0.5 pounds mass per hour per horsepower, per brake horsepower. So that would tell us if I had 10 horsepower, then this would be 5 pounds mass per hour. So this tells us what the fuel rate is, measuring the brake power coming up. And we're given as well that the BHP is 115 horsepower. The IHP is equal to 140 horsepower. And the ideal thermal efficiency is equal to 47%. So in some problems you'd calculate this knowing what the cycle is, but here we're given this. So now we're going to go find various efficiencies and some other information as well. And so let's look now and find the various efficiencies. The mechanical efficiency, eta sub m, is equal to BHP over IHP. So it's equal to 115 over 140 is equal to 0.821. So the fluid indicated it did 140 horsepower of work. It got converted into 115, so the difference between the two, 25 horsepower, was lost to mechanical friction. And windage with the rod going around in the air, there are all sorts of dissipated losses. The fuel flow rate, m dot f, is equal to 0.5 pounds mass per hour per brake horsepower. times 115 brake horsepower is equal to 57.5 pounds mass per hour. Then we could find the brake thermal efficiency, bhp over m dot f h sub rp. And this is why I said you have to look up the definitions, because they mix around very easily. And so we have 115 horsepower times 2545 BTUs per hour for horsepower. So one of the things I wanted to do by introducing this is that if this is in BTUs per hour, because I have this in pounds mass per hour and the heating value in BTUs per pound mass, that's going to have that term be in BTUs per hour. So then I need this in BTUs per hour. So there are 2545 BTUs per hour per horsepower. And then I know the mass flow rate, which is 57.5 times 19,000. So I have BTUs per hour above and below, and we have the brake thermal efficiency is equal to 0.267. Now we have some more things to find, so we can find the indicated thermal efficiency. So it's 140 times 2545 divided by 57.5 times 19,000. So that's going to be 0.326. The brake engine efficiency A sub B is equal to W dot B over W dot theoretical. And now I need to find W dot theoretical, and we were given the thermal efficiency. So W dot theoretical is equal to the thermal efficiency times m dot f h sub rp. So we have that, so this is 0.47 times 57.5 times 19,000. And that's going to be equal to 513,475 BTUs per hour. And now if I divide that by 2545, I'll get it in horsepower. So W dot theo is equal to that number, 513,475 divided by 2545. And that's equal to 201.7 horsepower. So now we have the theoretical horsepower. So we had the theoretical is 201, 140, and 115. And so we have those various horsepowers or energy outputs. So now A sub B is equal to bhp over theo hp. So this is 115 over 201.7 is equal to 0.57. And the indicated value is 140, the indicated horsepower, over 201.7. And that gives me 0.694. So I have that. And now we wanted to find the mean effective pressure. So and with mean effective pressure, we find this for the indicated work and the brake work. And so, but first we have to find the piston displacement. So P sub m is equal to W dot divided by V sub PD. And so let's find out what this V dot sub PD is equal to pi over 4 d squared, so 3.5 over 12 squared, so that's d squared, pi over 4 d squared L, 3.5 over 12, so this is L, times 6 cylinders, times 3,000 RPM. And so with that, we get that V dot sub PD is equal to 350.8 cubic feet per minute. And now I can find the indicated work, the indicated mean effective pressure. So I have 140 horsepower times 33,000 foot-pounds force per minute, the horsepower, divided by 350.8 cubic feet times 144 square inches per square foot. So I wanted to put in all these numbers so you could see them instead the units cancel out. So I'll get the indicated mean effective pressure is equal to 91.5 psi. So this is just psi. It isn't psi-G or psi-A, it's just psi. And the brake mean effective pressure is equal to 115 times 33,000 divided by 350.8 times 144 is equal to 75.1 psi. And now, so you're not the only one having this, here's some homework. So homework, 13.35, 13.37 A and B, 13.43, 13.19 star, so you have English units 13.21 star.